So we're going to do a quick introduction to reverse engineering, although this is not going to be quick since I've got a couple of hours here. But we are going to, let's see if I can turn that on, and yes, yay. We are going to talk about what reverse engineering is. We will also discuss a little bit about why you would do such a thing, some of the hardware and software tools that we'll use in the reverse engineering process, some of the impediments that various manufacturers will throw up there to try and slow you down, and the general process for being able to hack into hardware and then hacking into software, as the case may be. And we'll actually finish up with a kind of a brief discussion of some protocol hacking that we did. Definitely an interesting problem set, and we'll get into all of that as we go through the material here. One of the big issues, though, is knowing when to declare victory. It is always a tough thing in doing reverse engineering. You're not quite sure when you've done enough. There's always something else you could potentially do. And it's really a question of when you know to declare victory, fold up your tent, and go home. And then, of course, we'll finish up with a little bit of where should you go from here. All right. So what exactly is the reverse engineering process? First of all, let's assume we're given a piece of hardware or software, as the case may be. We want to deconstruct it. We want to find out how it was put together. We want to find out how they built it, what kinds of things are inside of it, whether or not we can extend it, and a few other issues we'll get into as we go through the material. Now, this will typically entail removing the case, repopulating connectors, disassembling the software, and it may require the use of hardware debuggers. We'll talk a little bit about that as well, and some other test equipment to figure out exactly what kind of connector we're actually looking at here on the motherboard. But I will put this out there and make sure, especially for you at home, don't do this at home unless you know it's legal in your jurisdiction. Here in the United States, we have this nasty thing called the Digital Millennium Copyright Act, and the DCMA gets really testy about disassembling firmware. So don't do that unless you have somebody's written permission, hopefully a law enforcement agency. Now, that being said, as we go through the material here, we will be talking about some techniques that in certain jurisdictions will get you arrested. Don't do them. I am not going to come bail you out of jail. And you can point to the YouTube video all you want. That's not going to do anything for you. This is the same sort of thing that I can explain how to make a silencer, but if I make a silencer, that's illegal. I will explain to you how to do reverse engineering, but actually doing the reverse engineering may be illegal in your jurisdiction. Please make sure you check that first. All right, so why do reverse engineering? Well, part of the goal may be to repair or repurpose or upgrade a particular piece of hardware that you may have. Or maybe you're just curious what's inside the box. Those of us who back in the dark ages used to take televisions apart and radios and things of that sort just to see what was inside of them, much to our parents' dismay. It was definitely something fun to do, and only occasionally, after it only took once, when you get across the anode of the television set and you get lit up by 35,000 volts, you only have to do that once before you respect that red wire. Don't touch the red wire. Now, often, and of course, part of this now is we're starting to see some ground being gained by the repair movement. The repair movement is a great thing. We should be able to repair those devices, especially phones. If we were going to spend $600, $700 for a phone and the battery goes dead, I'm sorry, I am not going to buy a new phone simply because the battery can't be replaced inside of the phone. We'll figure out a way to get in the phone and replace the battery, and we'll do all of that, again, within the limits of whatever our jurisdiction may be. There are going to be cases. Now, this is something interesting, and we found this happening more and more often. It's referred to as archaeology. Now, whether it is because somebody made a device, and when they made the device, they lost the engineer that made the device. They left, they forgot to document it, The documentation was in a package that was installed on a server, and the server went buns up and they can't get to the package anymore. Or the same thing happens with software. I've had cases where they need to figure out what the software that they wrote actually does. And it's oftentimes many years after the development of the software, and nobody remembers exactly what they did or how they did it, and it's not documented, and all those happy things. Those are all reasons why you might have to go in and take a look at an existing device to figure out what it does and how it works. Now, the other possibility is you might be presented with a suspicious device. Let's assume something fell off a truck and showed up at your back door. Well, what are you going to do with that device? You're certainly not going to plug it into your own network, I hope. You never can tell. Now, in this particular case, actually that picture that you see right over there, that hot spot right there, that's an actual chip under another chip. That motherboard was specially modified by somebody that happened to come as a commercial device. And when we popped open the box and started looking at it in an infrared, we said, wait a minute, this chip's a lot hotter than it's supposed to be. I wonder what's here. And you start taking a look at it, and it turned out somebody had actually hogged out a small space underneath the existing part and put something special there. Now, obviously, that kind of thing shouldn't happen all that often, but it does. And we're actually starting to see quite a bit more in the way of counterfeit equipment coming out of certain locations in Asia. This counterfeit equipment, some of it is really interesting. You'll look at the real part and it has silver solder leads, and the counterfeit part has copper solder leads. And it's the only visible sign that you have that it's actually a counterfeit. These kinds of things are starting to happen more and more. General rule of thumb, never buy anything off of eBay that you think is going to go into your corporate infrastructure. Just a suggestion. Now, there may also be some special software on a device that you're concerned about, whether that's malware, spyware, or govware. If you happen to be, now what's govware? Govware happens to be something that we find in the German-speaking countries. The Swiss have Megapanzer, and the German government has one called R2D2. And these are legitimate pieces of software that the government installs on your machine when you're asleep. And at that point in time, they are keyloggers and other things that they track you and see what you do. And if you've been talking to people you're not supposed to talk to, they will come knocking on your door. And GSG9 is very unfriendly with the MP5s as they kick in the door, as a general rule. Don't do that. That would be bad. But govware is certainly a thing. We have actually found one special thing that I can share with you. There was a set of equipment from a large manufacturer of equipment of computers. And this particular large manufacturer had sold a whole bunch of computers to a defense contractor. And the defense contractor, as part of their normal modus operandi, take the equipment and put it into a sandbox. They basically put it into a small, isolated network enclave, and then they start dorking around with time. And sure enough, after about 6 months of time, it beaconed out and went back home to China and said, hello. They, of course, asked the manufacturer, what was that? The manufacturer said, oh, it came from the original design manufacturer that way. So the fact that they were actually subbing the work out to a place in China that was doing all the BIOSes and everything, it was a weird situation. We actually tracked it down a little bit further than that. And what it turned out was they were using the system management mode on the x86. And in system management mode, it's built specifically to allow you to take a look at temperature and power rails and things of that sort. It's made for the server world. It's a non-maskable interrupt, so you can't turn it off. And what was happening, if you switched into system management mode, there was a TCP stack in there, and it was phoning home. So little things like that, yeah, you should probably keep an eye on them. I always am suspicious of any new equipment that I get, but I tend to be paranoid anyway. At least that's what my wife will say. All right, so what kind of tools should you have in order to be able to just simply disassemble the device? First of all, you're going to need a Torx driver set. Torx is one of the more popular weird screws that are used in a lot of these cases. But you'll need screwdrivers of various sizes, a precision utility knife, not to use the trade name that you all know so we don't want to do that. But a precision utility knife, spudgers, these are basically little pry bars, plastic pry bars. Guitar picks work really well. Suction cups, small hex drivers. Thankfully, thanks to the Right to Repair movement, these are all available as a kit. You can go to ifixit.com and you can get that little kit that you see there in the upper right-hand corner, that little thing right there. That is a really incredible thing. Now, one of the things that you probably can't recognize is that little black thing that looks like a hot dog, about that length. That's a really cool device. That is a piece of, it's a squishy, it's a squishy slug-like thing. You put it in a microwave for about 30 seconds and it heats it up. And then you slam it on the back, well, you don't slam it, but you place it on the back of the device you're trying to unglue. And what it does is it transfers enough heat to the glue to soften it, so that you can then pull the back off of machines, off of devices like, iPhones, that you're not supposed to pull the back off of. And that's also where the suction cups come in, by the way. You use a suction cup to pull it apart. Those are all things that definitely handy to have. Another thing that you can do, of course, if you happen to have something that you know has an adhesive in it of some sort, heat guns. If you happen to have solder equipment and you've got a heat gun, that'll work. Blow dryers, if you don't happen to have a heat gun, or this microwavable gel, you'll heat the adhesive up, and then that will make it pliable enough that you can get the box, that you can actually get the box open. Another thing that's really handy, and this is one of those things that you don't really realize until you get into the business, and that is an inspection microscope. You really need to be able to read those teeny tiny little letters on certain parts. And even with my bad eyes with 3 or 4x magnification, I still can't read them. So these little inspection microscopes, they're USB powered. You can actually use them to take pictures of things. So if you need to prove to somebody that it was a particular part, you can actually take a picture of it. And they go up to 600 power magnification. So it does a really nice job, and definitely it's handy to have one of these things around. Now, electrical test equipment, especially when we're trying to figure out exactly what kind of circuits are in the box and what voltages they're running. A volt-ohm meter is a must. Don't scrimp on these. Spend a little bit of money, get a decent one. They'll typically cost you, a really good one will cost you anywhere from $70 to $150. The one that you used to get at the old Radio Shack, for those of you who are old enough to remember Radio Shack, the $9 meter, yeah, no, that one doesn't work very well. I still have some of those, and I just use them to tease my robotics students. Here, try this. Oh, what's this meter? What's this little, it's got a little needle on it. How do I read that? The problem with LCD-based meters is oftentimes the event that I'm looking for happens so quickly that it can't update the screen fast enough. So there's a voltage change there, but it's so quick that I can't tell what the voltage change was. If that is the case, and oftentimes it is, then we drop to a digital storage oscilloscope. Now, if you're a software person, go into your hardware developer one day and ask to hook up the digital storage oscilloscope, and he will look at you like you have two heads. And why do you even know what one of these things is, let alone want to hook it up to something? A DSO is a really handy application. We'll see a couple of pictures of where I used a DSO to take a look at a signal. And it turns out that, yeah, you can spend a lot of money on these things. I mean, tech's got some wonderful scopes. You know, a 4-channel, 2 gigahertz scope that'll set you back $30,000. But the reality is 50 to 100 megahertz is good enough for most applications, most of these kind of applications at least. So that means you can probably pick up a couple of $100 scope and it'll do okay. Now, some of the little PC scopes that are USB powered, some of them are not quite fast enough because they're only in like the 5 megahertz, 10 megahertz range. Usually 50 megahertz or so will allow you to catch most things that might be of interest. Another little gizmo that's handy to have is an 8 or 16 channel logic analyzer. This one is one of the ones that is powered with USB. This is my Saley. I've got a wonderful, I love my Saley. It is a USB 3. I've got the Saley Pro version, so it's got a USB 3 interface on it. When you got to transfer a lot of data really, really quick, USB 2 doesn't cut it. But USB 3 does a great job. Now, another thing that's handy is a SIGROC compatible signal identification interface, AKA Bus Pirate or something similar. These are often, we'll use these as a way of just being able to try and identify the type of signal that it is. Is it a JTAG? Is it a serial port? Is it an I2C? What is it? Because if you start plugging things in without really knowing what it is, you'll likely let the magic blue smoke escape, and that's bad. Not to mention the fact they come in and go, what does that smell? No, I took a shower. It's not me. It's that thing. Okay. Now, logic analyzers as protocol decoders. Most of the high-end logic analyzers these days have got protocol decode in them. They've got I2C, SPI, CAN bus, asynchronous serial, etc. The tricky part, of course, is just identifying the signals. Also, these devices tend to have their own limitation as to what kind of power you can put across them. 5 volts is a maximum, and we have seen 12-volt compatible RS-232 interfaces. So the old RS-232 standard actually used to go to 12 volts, and you'll find equipment sometimes that still does. So definitely you got to watch out for things like that. And some of the really expensive units of these will decode both PCI Express and other high-speed buses. This particular one, this happens to actually be from my Saley. The Saley will do 10 megasamples per second or something like that. So it's fast enough for most things. Now, I have a couple of patents on doing video backup out of your video port. Back in the dark ages, we used to do things like that. And I had to use high-speed echo logic to do that. So 2 gigahertz logic analyzers and scopes where the empty mainframe of the logic analyzer, nothing in it, just the mainframe, is $35,000. So fortunately, you don't have to have anywhere near that kind of investment in order to be able to do this. By the way, the Saley, the 8-port Saley, I think is $495, something like that. It's relatively inexpensive for what it is. Maybe that's the 16, is the $495. The 8 may be a little bit cheaper. I don't remember right offhand. It's been a while since I bought mine. Okay, so now that we got all these tools collected, now what's the thing that we want to do? First of all, we need to do a little bit of research. We need to find out, is there an original design manufacturer someplace, an ODM? And if there is an ODM, who is it? For instance, with laptops, it's common to find laptops made by a company called Clevo. They'll be branded with Dell or HP or some other badge on the outside of them, but they're actually made by Clevo. Why is that important? Well, it's because you're looking for the FCC ID. If you look in the device, you will find somewhere an FCC ID associated with it. Now, the Federal Communications Commission here in the United States has requirements for any device that could potentially emanate in the spectrum when they were doing a certification for a Class B or Class C type device. They will have an FCC ID associated with them. The FCC ID is, you can look it up on fccid.io, among other places. You can actually go to the FCC, but it's so hard to find it there. But there are other websites that you can actually look up the FCC ID. The advantage of finding the FCC ID is that you will find that a lot of devices use the exact same components. In particular, radios. Radios, I actually talked to a manufacturer, a Chinese manufacturer one time about where's the break-even point for being able to make my own radio? At what point does it make sense to do that? And they go, well, after FCC certification and all the stuff, the registration and everything you have to go through, break-even point is about 1 million units for your own radio. So what happens, many manufacturers don't use their own radios. Manufacturers will go to another vendor that has an already approved radio set. And this already approved radio set has an FCC ID associated with it. You look up the FCC ID and you find out it's the exact same radio that's being used in like 10 other devices. That's an advantage because one of those other devices may not necessarily be as locked down as the one you're looking at. It may actually have more open source code associated with it. There may actually be some U-boot versions and things of that sort floating around for the other units that you can then look at those and try to figure out what does that mean to me for this device that I'm having a look at. Another one, which is kind of an odd one that you wouldn't normally think about, and that is, are there patents involved? Does the manufacturer of this particular device have any patents associated with it? Patents are a wonderful thing. When you go to the US Patent and Trade Office or you go to the EU Patent and Trade Offices, the patents are public record. And when you bring up the data sheet of the patent, you will find all kinds of interesting stuff in there. Circuit diagrams, box layouts, which parts are being used for which motherboards. There's all kinds of really cool stuff in patents. And another one that you want to take a look at is who are the patent holders? And see if you can find out any information about them. The reason I say that is because when we get into the disassembly of the protocol, we'll find out that it was something specific to the patent holder that actually made its way into the protocol. Interesting problem with that. So patents. And a lot of people who are just starting to do reverse engineering forget to check the FCC IDs and forget to check the patents. Both of those are tremendous sources of information. All right, so now opening the case. Just opening the case can be a problem. Sometimes manufacturers will actually sonically weld the case. And if they sonically weld the case, getting into it is a Dremel. That's one of those tools that I didn't mention before, but sometimes it's handy to have a Dremel just to cut through the case. Now, why do they make it so hard? Well, sometimes they don't want you to see all the goodness that's inside. In other cases, they don't want you to see all the badness that's inside, like that one right up there. That is probably one of the worst solder jobs I have ever seen in a commercial device. And that's actually considerably cleaned up over the first 2 versions that they made. Cold solder joints, I mean, it was just horrendous inside. And you just go, well, if nothing else, I might just fix it just while I'm here. Because I can't stand to look at such bad solder joints. Ugh. All right, other techniques that are designed to keep the casual user out of their hardware. One is special screws. We see there a picture of the pentalobe screw. That was one that Apple made that would keep you out of the iPhones. It turned out there were only 2 pentalobe screws in the iPhone. It was in the base where the USB connector was. But it was a special screw that they had custom made, and it took at least 2 weeks to fab one out of a 3D printed material. Usually you'll see Torx. Torx screws are very popular. Make sure you have a complete set of Torx, especially the little tiny Torx. They are really tough to get a hold of and used a lot. There is a secure Torx, which has a little post in the middle of it that keeps a normal Torx screwdriver from going into it. So if you go to a Fry's or you go to, and not so much Best Buy, but Micro Center, some of those places, they'll actually have security tool kits that have all these weird little screwdrivers inside of them. Definitely worth the $10 that it costs to buy one of those. The tools themselves are not all that fantastic, but when you need something that's got a secure Torx, you need it. You need it then and not have to go try and find it. Yeah, absolutely they are. Now, of course, sometimes they'll use special adhesives. That was what we were talking about earlier when you use the heat gun to kind of melt the adhesive down a little bit to make it a little more pliable. Anti-tamper sensors. Now, anti-tamper sensors are really tricky. What they'll have is a case that has some special switches inside of it that if you open the case, it triggers the switch and zeroes out the flash. That is particularly troublesome. We'll talk more about that in just a minute. And the other trick that they do is encasing the device in epoxy, otherwise known as potting the device. That's that black gooey thing that you see right there. And they do that for several different reasons. One of them is to keep you from figuring out what the circuit is. Other times it's to keep it from getting wet. If it is going to be in a moist environment, we'll want to keep the circuitry dry, so they'll do an epoxy coat like this. Or if you happen to be going into space, it's called conformal coating, and it'll keep your devices from outgassing. We do a lot of work in the space world, so it turns out that happens quite a bit. So you have to basically conformal coat it in order to get it to keep it from outgassing and then blowing the chips up. Now, dealing specifically with anti-tamper switches and potting, any well-equipped reverse engineering shop will have an X-ray inspection capability. So it's an X-ray machine, and basically you just simply put the device under the X-ray and you take a look at it, see what it looks like in the X-ray world. That will typically let you know that there may in fact be some tamper switches inside of it. One of the things we have found with tamper switches is liquid nitrogen does a great job at slowing them down. You hit it with liquid nitrogen through the case, and then you pull the top off, and the switch is now basically frozen. You can now put tape on it, and the switch won't trigger. So liquid nitrogen, great to have around. Not only that, but it's fun to play with, and you can make great ice cream with it when you're bored. Now, potting comes in several different varieties, including special polyesters and epoxy resins. When you get to the potting, you can actually kind of put your finger in it. You can determine whether it's a hard pot or a soft. And depending on the type of material that it's made from, oftentimes heating will make it pliable. So this is one of those cases where just putting it in an oven at about 200, 250 degrees Fahrenheit will make the potting pliable enough that you can actually pry it off. Be careful with this, because as you heat this thing up, first of all, understand that you're using, most likely today, you're using Rojas solder. So Rojas solder is a new type of solder, it's lead-free, but the melting point of Rojas solder is around 700 degrees Fahrenheit or so. So you can heat the board up to about 250 degrees Fahrenheit, and it's not going to have any damage to the actual solder in there. The other thing that you may find is, of course, when you do that heat, make sure you have it well ventilated, because some of these epoxies have toxic fumes that come out of them when they start heating up. So definitely watch out for that. There are solvents that will often do this. WD-40 actually does a pretty good job against several different types of epoxies. Dichloromethane, nitric or sulfuric acid, isopropanol, all of those are types of materials that can be used to dissolve potting. The problem with a lot of this stuff is it may require special permits in your jurisdiction. You can't just simply call up and say, hey, I'd like to get a gallon of sulfuric acid. Most of the chemical supply manufacturers take a dim view of that sort of thing and start asking a lot of questions. Why do you want sulfuric acid? And what are you planning on doing with the sulfuric acid? And when you start trying to explain to them that you're reverse engineering a piece of government equipment, they then take a dim view of that, and they don't ship it to you. But nitric acid certainly is something you can typically get your hands on. Sulfuric is a little bit harder. This stuff that you see there called a tack, that is actually a pretty decent material. It's not cheap. That little liter can there is almost $100. But when you need it, you need it. And it'll actually do a really nice job of pretty much dissolving the material. Now, when all else fails, you go to cut and scrape. Cut and scrape is a Dremel and an X-Acto knife. A precision utility knife. It's not pretty. You see an example of it down there, cut and scrape. But unfortunately, if you can't get the epoxy to melt any other way, you may not have a choice. And of course, be careful as you're using the Dremel to scrape off, sand off layers, because sometimes it produces fumes. Sometimes the little particulate matter, if it gets into your lungs, is really bad stuff. So make sure you wear a mask when you're doing this kind of stuff. In general, anytime you're messing around with epoxies and polyester resins, you want to wear a mask. It's really pretty much generally nasty stuff all the way around. Now, let's assume that we have managed to get ourselves into the device. Now that you got it out of the case, let's take a look at the device to see if you can identify the parts. Oftentimes, if you look at the parts, some cases I've had manufacturers black out the part number with a Sharpie. Other cases, and if you hit it with just the right light, especially if you're in different modalities like infrared, you can usually read it even though they've marked it out with a Sharpie. Or if you, I have seen them actually scrape the part numbers off to try and keep you from figuring it out. And again, in that case, a little bit of nitric acid will usually bring the part number back up so you can figure out what it was. So being able to read the part numbers is easier said than done. But if you can identify the part numbers, try to get a hold of the data sheets. In some cases, the manufacturers will be more than happy to give you the data sheet. Marvell will give you a data sheet, or Atmel or one of those guys will give you a data sheet. Others, not so keen on giving data sheets. Intel, for instance. Anybody from Intel in here? I'm sorry. Intel, if you want to get data sheets from Intel, it requires your firstborn child, and you then have this book that is basically handcuffed to you, and you can't go anywhere. You can't leave the book because the book gets lonely, and you have to carry it with you all the time. It really is kind of a nuisance in some of the cases for some of their parts. But absolutely take advantage of teardown sites like iFixit. They have already done, if they've already done the teardown for you, that's fantastic. Saves you a lot of time and effort. In some cases, they'll even identify some of the really weird chips. It's a Samsung part that's not commercially available. It's only available for company XYZ, and they'll give you a little bit more of additional information about it. So that's really handy if you can get a hold of that. Now, getting that sample data sheet is important, and the reason it's important is because it'll tell you capabilities of the part of the major chips that you may need to know. For instance, in this particular case, we were doing a job that used an AVR. It had an AT Mega processor in it, and the fact that we were able to take a look at the data sheets and find out that there were actually 2 serial ports involved in that particular part, we then could figure out a little bit more about what the serial ports were doing. What they were up to with them. Additionally, they may very well talk about SPI flash interfaces and things of that sort to give you an idea of how the board is supposed to boot. And then if it's a SPI flash, we can then hook onto the SPI flash and try to read the flash directly. But more importantly, it gives you some information about voltage levels, logic voltage levels. We see today, we don't see much in the way of 5 volt anymore. It's usually 3.3 volt or even all the way down to 1.8 or 1.2 volt logic. So you definitely need to do a little bit of homework there, because if you try to plug in a 5 volt RS-232 port into a 3.3 volt logic level port, it'll toast it. So definitely a bad thing. Data sheets may also outline a lot of information about the algorithms that the part supports. If it supports things like CRCs or anything special that may be built into the hardware. Sometimes the manufacturers will take advantage of that, and it will explain a lot of what you're seeing when you're looking at it on an oscilloscope. All right, so now repopulating the interfaces. Of course, a lot of manufacturers will depopulate the debug and the serial interfaces. So the JTAG interfaces in particular will be depopulated at a minimum. Sometimes you'll find the serial ports are depopulated as well. JTAG interfaces often have a pretty familiar look about them. So it'll be a 10-pin or a 14-pin or a 20-pin connector. Those kinds of things kind of stick out on the board, and they're fairly easy to find. Also, again, kind of a caution here about the logic voltage levels. In this particular case, we put this scope on it. If you use a digital signal storage oscilloscope, we have high voltage probes that are available for that. So when you put that on the circuit and you're taking a look at it, you know you're not going to toast the scope. And the scope is made to be able to sample the voltage level, so we'll be able to see it. And in this particular case, for this one, this is actually looking at a communications channel, and what you're seeing there are ones and zeros going across. And also, because of what it looks like, if you actually could see it very well, you'd see that that is a little bit over 3 1-volt markings. So we were looking at 3.3 volt logic in this particular case. Also, of course, a signal tester like a bus pirate can oftentimes determine what kind of signal it is, whether it's a serial port or a JTAG or something along those lines. They actually have some pretty decent tutorials for bus pirates and similar sorts of devices. And of course, sigrock.org is a great site for kind of information about how to do this kind of signal analysis. Of course, for those of us who do board ports, where we're trying to port Linux or VxWorks or some other operating system to a new platform, we need these kinds of things because we need to be able to see what the circuits are actually doing and whether or not our code is actually doing what it's supposed to do. So definitely really handy to have this kind of stuff. Now, other cases, we'll actually see a lot of examples. Here's some examples of devices that have had to be repopulated. That's a router up there, and it turns out that they had 4 pins. Normally for a serial port, you'll have transmit, receive, and ground. So that's 3 pins. Occasionally, you will find a power pin sitting next to it. So again, this is one of those, okay, make sure you test the pins before you start plugging anything in to know which one is the power and which one is the ground. UART serials, JTAGs, I mean, here we see this particular one over here happens to be a JTAG signal. We have another serial port in here. This is the Pocket Beagle. If you look on the back of the Pocket Beagle, they actually have a JTAG interface there. Now, this connector that you see, this is referred to as a needle connector or a pogo pin connector. The little pins that you see there are spring-loaded, which is why they call them pogo pins. And what you'll do is there are a couple of holes on either side, and you clip this thing in, and then it stays in contact with the connector. So we see this being used a lot in microcontrollers. So whether it's an ARM, Cortex M3, Cortex M4 type microcontroller, oftentimes they will have some of these pogo pins. Additionally, we're starting to see more prevalence of serial wire debug, SWD. SWD is basically JTAG, but it only requires 2 pins. Instead of 1149.1, IEEE 1149.1, I think it's 1149.7. So they have a specification for this thing. Generally, the serial wire debug is targeted at microcontrollers, but we're starting to see it now on some of the larger ARM Cortex-A parts as well. So, and if we had a requirement for serial wire output, which is basically a print line, it's a serial port, that requires just 1 more pin. So in 3 pins, we can absolutely get basically debug interface, et cetera. Now, some of the manufacturers will actually blow the E-fuses. So what the heck's an E-fuse? An E-fuse is an electrical fuse that's on the chip itself, and when they blow the E-fuse, it basically breaks the connection to the debugger. If they've blown the E-fuses, the only way to fix those is to decap the chip, and with a laser, you spot weld the E-fuse back in place. That clearly is not something that the typical user has at home. because they basically have to cut the top off the chip and then look at it in an electron microscope, figure out where the fuse is and zap it and bring the fuse back. So that's not something that most people can do, but nonetheless, hopefully you don't get to that level. Now, here we actually see two connectors side by side. One of them is a 14-pin connector and the other is a 10-pin connector. The 10-pin connector happens to be two serial ports. The 14-pin connector is a JTAG. You will also notice that all the holes are nice and neatly filled in the wave solder. So when we get ready to repopulate the connector, we're going to have to get through that and actually solder the thing back in place. So that can be a little tricky. All right, so now why bother repopulating the interfaces? Well, of course, for serial ports, the goal is to be able to watch the boot cycle. We want to know what this thing does during the boot cycle. We want to know if it's using U-boot. We want to know if it's using some custom home-rolled bootloader. Of course, for JTAG and serial wire debug, the goal here is to be able to read the firmware out of the boot flash. We want to be able to grab all of the firmware because that's going to have some interesting binary blobs in it that we probably want to take a look at. And we'll show you an example of what that looks like here in a moment. Now, once you have the firmware, you can now start the reverse engineering of the boot code. Which bootloader is it using? Is there a device tree blob? Of course, for those of you who do a lot of work with the Linux kernel, you know how important it is to get that device tree blob. If you don't have the blob, man, your life is living hell. So being able to pull the device tree blob out of the firmware can save you a tremendous amount of time. Obviously, if you're trying to upgrade the device, let's say it had a 2.6 kernel on it, and now you want to move to a 4.14 kernel, you're going to have the device drop blobs because they started using device blobs in about the 3.10, 3.14 time frame. So in order to move up to a significantly newer kernel, you're going to have to figure that out. For those of you who don't know what the device tree blob is, it's basically a way of describing the motherboard and the components that are on the motherboard. So you'll know there's two serial ports located at this address. There is megabytes worth of memory located at this address. There's an I2C, there's a SPI bus, all that sort of business, GPIOs. All of that will be laid out in the device tree blob. So if you can get a hold of the device tree blob, that's a huge win. And of course, which OS is it using? It may not necessarily be using Linux. It could be using VxWorks or free RTOS or some other flavor out there. And if you find out that it's using something like Linux, then which version of Linux is it? There's been significant changes between the 2.6 kernel and the 4.4 kernel. So, as a consequence, knowing which version of the kernel it was running is a huge thing to be able to take into account. Now, another thing is, of course, being able to repopulate the interfaces and use a JTAG to read the flash and get yourself a hold of the binary, that's all very sexy and wow, that's incredible you were able to do that. But sometimes it's not that hard. Sometimes you just go to the manufacturer's website and they will have updated firmware or even old firmware. If it's an older device, they'll have the firmware sitting out there and you can download it. And when you download the firmware, well, okay, now I just saved myself all the trouble of repopulating the JTAGs and all that sort of business, but I have the firmware. If you do have a case for firmware update, then download it, take a look, see what's in it. And we'll show you some tools that help you do some dissecting of that here in a moment. But depending on the vendor, you might just be able to download the update directly. Occasionally, they will require you to actually do the update through the device. So if they're going to do it through the device, then make sure you've got your Wireshark turned on so you can capture all the packets that go through and reconstitute the actual firmware image from the packets that got transferred in order to download it to the device. A little bit trickier to do that, but certainly if you're dedicated, it's not that hard. All right, so now that I have the image, here we have an example of this little guy right here. This is an Action Tech MI424. This one happens to be, I think this is a Rev F or something, Rev G maybe. But it's one of them that I had laying around the house because Verizon forced me to upgrade, and therefore I had this extra router sitting there, so I might as well do something with it. And when we took a look at the firmware, we actually found that Action Tech does not supply the firmware because it was developed specifically for Verizon. As a consequence, we had to go poking around in other places to try and find a copy of the firmware. We finally did. It actually only took us about an hour or so to research and find out where the firmware was. And then we downloaded the firmware. Having the firmware, now you'll notice that this is in a weird format, a .rmt format, which is some sort of remote format. It's a strange format, doesn't correspond to anything. It's something that's proprietary. But that's okay, because it turns out that our good friend Binwalk, and if you're not familiar with Binwalk is a great tool for looking at binaries and kind of walking through the binary to try and find out what's in it. We took a look at Binwalk, and sure enough, there's a U-boot header out there, which identified the type of processor it was and exactly what kind of kernel it was running. Then we saw a gzip compressed data segment, which is probably going to be something like CramFS or some other sort of compressed file system. And then we found that there was a wide area network firmware interface sitting out there that if we were really interested in going a little bit further in there, we would have dug into that Landcom firmware interface to try and figure out what was in there. But we will see that we didn't really have to get that far in order to be able to do some interesting stuff here. Now, once we know where the edges are of the different images, now we can use a tool like DD to simply extract the pieces out. So here's an example of separating the pieces out of that firmware. We went out, and the first part of it, of course, was U-boot. So our block size is 1, and we told it to skip the first 163 bytes, which is what this told us to do in the decimal here. That's 163. So we skipped the first 163 bytes and then basically wrote out until we got to the next block that incorporated all of the U-boot stuff. Did the exact same thing for the compressed file system and, of course, the Landcom firmware just for completeness. So that now we have all 3 of the pieces that are laid out. Now let's start poking around inside there. Because it identified itself through Binwalk as a gzip compressed image, we simply extract it out and then unzip it and see what's in it. And guess what? Once we did the unzip and then we did a Binwalk on that, we found gzip compressed data, we found 2 CramFS file systems, a whole bunch of security certificates, we found CRC polynomials for doing the checks. We found that it was a Linux 2616.14 release of the kernel. When that was made, that was dated back to 2014. And we also saw some of the paths for the actual files inside of it. We cut it off because there was a whole bunch of stuff in there that we couldn't make fit on the screen. Even that was a little hard to get fit. But that was a really fortunate find where you managed to just simply, by grabbing a hold of the firmware, doing a little bit of poking around in it, figure out that it was a gzipped environment, un-gzip it, and then run Binwalk on it again, and you find all the good stuff that's inside of it. So now, what's the general approach to reverse engineer a binary? Well, we got really lucky with the MW424 part. That firmware was just fantastic because of the way they laid it out. Most firmware is not so forgiving. Now, you will find that some of the firmware from manufacturers, if you can download the firmware, it may be encrypted. If it's encrypted, then that represents a much more difficult problem. Sometimes it's just compressed. And oftentimes, it's one of these security through obscurity kind of things. They compress it, and of course, they don't figure that anybody can figure out that it's compressed, and therefore they don't know how to decompress it. But when we take a look at it, we run Binwalk, and we have it print out the entropy. Now, the entropy, if you have an entropy close to 1, that means it's typically either compressed or encrypted. And when you see entropy like that, you go, okay, but at least it didn't start at 1. There was some little piece ahead of it that was not 1. So that gives you some hope that there's some way of being able to figure out what's inside of it. Then another tool we'll use is the strings command. Once you've compressed it and you run strings across it, you'll find all kinds of stuff in there, like this thing here, start section, RG hardware, Ferocion, distribution, the vendor, Verizon, the product version, et cetera, et cetera. That was all in there just through looking at the strings, yeah.
How often do you find that the manufacturer is grabbing these chips out of the strings?
The question is, how often do we find the manufacturer strip the strings out? If the manufacturer is doing their due diligence the way they should have stripped it. Sometimes they will, sometimes they won't, and it's just catch as catch can. You may get lucky, and if you get lucky, take it. If you're not lucky and you get nothing but gobbledygook out of the strings command, it's like, well, okay, we tried that, and that didn't pan out for us, so let's move on to the next thing. Now, the next step, once you've got it separated out a bit, then we can take another look at the entropy. After decompressing that image, we see a spike right there, which is the separation between the U-boot image and the rest of the CRAM-FS. These entropies close to 1, and those are the CRAM-FS images, and then we see the rest of the operating system sitting out here. So again, if it's not solid at 1, that's good. If it's solid at 1, that's a bad thing. That means they've either encrypted it or they've got something else sitting out there that makes it look like encrypted data. Once we, of course, in this particular case, we did the bin walk on it. We found out there were 2 CRAM-FS images in the front. We know what their offsets are. Because we know what their offsets are, we can simply mount them and take a look at them. That's a really nice thing about the way the loopback interface works in Linux. If we can identify what the file system is, we can simply loop back mount it and then take a look inside. CRAM-FS is compressed, but not the headers. So the data is compressed, but the headers are visible. So you can then look at the names of the files inside of CRAM-FS. When you go to Squash-FS, it's a little bit different. Now we'll see a lot more Squash-FS being used. A little bit harder to do the dereference on, but not impossible. But in this case, we were lucky. We got CRAM-FS, and it was easy to go ahead and mount it. Now, normally we would then dig a little bit further into that, go ahead and mount them and try to extract things. We'll do that some other time. We just don't have time to mess around with it here in this class. All right, so now let's take a closer look at the binaries. Let's assume we've managed to be able to get the binary out of the image. What can we do with it? Well, first of all, there are bin utils like obj-copy and obj-dump, which will allow us to do a disassemble of the data. If you look at obj-dump, obj-dump has the -s option that'll allow me to disassemble the data. So this is really useful. If I know the manufacturer, if I know it's a MIPS or an ARM or a PowerPC, whatever, then I get the object dump for PowerPC, and I do an obj-dump-s against that image, and it will then disassemble the image for me. Understand that disassembling the image is useful, but in some cases not terribly enlightening. Unless you speak the assembly language of the native processor. If you speak the assembly language of the native processor, then you've got all kinds of stuff there. Also understand that when you run into something like that and you've disassembled it, there are not going to be any nice, neat labels. There's not going to be, basically the object code is stripped. So you will find a jump instruction to some random offset or some offset from where it is right now, a relative offset rather. So when you're in that situation, you basically have to try and create a map of the executable from the assembly language. Now this is definitely a long pole to try and go through. If you can avoid it, absolutely try to. This is why we love open source. It is a wonderful thing to be able to say, well, I need to get the open source from you. And then you can do a mapping between the open source output and the actual executable. Obviously, when you're dealing with open source, you can get a hold of the compilers. GCC is often the compiler that's used, simply because it's free. And the manufacturers don't want to have to spend $1,000 for a development environment. So it works out really well that way, and everything just comes out as normal ELF with GCC as the primary compiler. All right, so now let's assume that I have my executable and I've taken a look at it and I go, okay, this looks all right. Now what can I do? Well, I can run it. If I happen to have QMU, for instance, for that particular processor architecture, then I can actually put it inside of a QMU session and try to execute the code. Using tools like strace and ltrace, we can get a pretty good idea of what the code is doing, what functions it's calling up in the kernel, what libraries it's trying to call as it runs. There are some disassemblers. There's the Isr project. This one is a fairly nice disassembler, does a great job for x86 64, and it tries to figure out exactly what the jumps are and help you put it back together again. There are also professional tool chains and disassemblers like IDA Pro. Now, IDA Pro is the hardcore reverse engineer's friend. IDA Pro is not cheap. It's like $6,000 or $7,000 for a copy of IDA Pro per CPU architecture. So it's not cheap, but it is awesome. What'll happen, you get the assembly language output over here, it will construct a calling graph for you and allow you to label things. So if you look at a particular piece of assembly language code, you can clearly tell that it's a print statement. You can actually label it as print. So when you're creating the calling sequence here, you can actually try to figure out what the calling sequences were, what code is calling what, the interrelationships between the individual function calls inside of it. Understand this code was probably C code or C++ code at some point, and now we're looking at the assembly language. So a lot of the things that would have been control structures inside of the C have to be mapped into assembly language control structures. We can also see the actual data itself down here, and in some cases we're looking for very specific byte patterns that indicate the end of a JPEG image, for instance, if they happen to have a boot logo or a splash screen in the unit, and you want to change the splash screen to make it really cool. Well, you want to find out where the splash screen starts and where it stops and figure out how much space you have and whether or not you can actually go out there and reprogram it. So all of that sort of stuff comes into play with IDA Pro. As I say, it's not a cheap, although you can get, I think, a 30-day evaluation of IDA Pro if you want to play with it. But they have training classes that teach you how to use IDA Pro because it is a complex enough tool set that you really need to take the training class. This is used oftentimes by larger name government agencies to disassemble malware and figure out what the malware actually did or what it's supposed to do. Always use protection. That's a general statement in life, but nonetheless, never run a foreign binary on your test platform without taking some significant precautions. First of all, QMU is a good start. Make sure you keep it bottled up. And of course, there is support for most of the common CPU varieties out there, especially MIPS, PowerPC, ARM, and x86. Or you could use a VM. If you've got KVM, certainly use that to keep the application bottled up. At a minimum, use a chroot LXC type environment. LXC rather than Docker, simply because LXC looks like a real operating system to the application as it runs. Docker tends to be so stripped down that the application says, well, I'm missing this. I don't have this library, blah, 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 blah. I can't run. Well, okay, if you're running LXC, chances are you can actually trick it into thinking it's running on a real operating system. Yeah.
Have you ever seen malware that purposely tries to act differently under a view?
Oh, yeah. Yeah. Yeah, it turns out that some malware will look at certain registers to find out if they're there, and Apple calls that the UEFI BIOS. No. I'll probably get in trouble for that. Cut that out. But they actually look for special registers in places, and if they don't find them, then they say, oh, I must be running under a VM, and therefore I don't run. So yeah, there is certainly legitimate pieces of code as well as malware that will look around inside the environment that it's running in to determine whether or not it's running on real hardware. In that case, you have to go in and dork around with your QMU register sets to make it think that it looks like real hardware. Sometimes easier said than done. Of course, capture the run with strace and ltrace. We want to see what it's doing. We want to see what kernel functions it's calling. We want to see what libraries it's accessing. Note any anomalous behavior. It could be a legitimate application, and because of the fact that it's the third Tuesday of the month, it does something weird on the third Tuesday of the month. They call that Microsoft Patch Tuesday. And now, yeah, cut that out too. I'm going to get in real trouble here. All right. Alternatively, you can transfer the application to a small platform. Now, let's say it's ARM. Then we can take a BeagleBone or a Raspberry Pi, and we can transfer the application to that platform and try to run it there. If something goes wrong, pull the plug. Simple enough. And you can always reformat the SD card and start over again, but if I'm running malware, I probably want to destroy the SD card and get another one. I don't want to take any chance that there's something left over. Even though you reformat, sometimes the bad block list and everything doesn't quite work the way you think it should. And it's also, I've seen malware that actually manipulates the bad block list. So definitely be careful about those kinds of things with SD cards. In general, don't run with internet protocol enabled. Don't have it connected to the internet. Pull the Ethernet cable or go into IP tables and block it off there. Block all the outbound traffic until you have a warm, fuzzy feeling about what it's doing. Again, putting it inside of a kind of a sandbox and watching it go back and forth. It turns out that in that case I was talking about with the major manufacturer and the BIOS chirping back out to China, that was no operating system running. That was just sitting at the BIOS, and it chirped out. So they call that beaconing, and this is a characteristic of a lot of malware. It'll beacon back home, let them know, hey, I'm here, this is my IP address, do you have anything for me to do? And the controller will say, go to sleep and call me in a week, or a month, or 6 months. And then it will wake up again, go back out, check to see if there's anything new to do, and then things will do some really interesting stuff. This is what you call intelligence, surveillance, and reconnaissance operations. With Isr Operations, we're interested in looking to create a map of your network. And creating a map of the network is really valuable because it then tells me that you have printer X and router Y and devices made by manufacturer such and such. And by that information, it helps me understand what sorts of attacks might be viable against that. So understand that the malware writers are trying to do that against you, in which case you definitely need to be careful with that kind of stuff. Now, we'll show you real quick here an example reverse engineer of a protocol. In some cases, it's not the device that we're really interested in. We're interested in the communications protocol that the device uses. Ethernet cabling, of course, just because it's got an Ethernet cable plug on it doesn't necessarily mean it's Ethernet. We see Ethernet cabling, those 8-pin RJ45s get repurposed. They're repurposed for serial ports. They're repurposed for all kinds of stuff. And it may not be standard 802.23 or 802.3.2. It may not be that. It may be EtherCAT, or it may be some other industrial protocol which happens to go across Ethernet cables. So when we're trying to understand exactly what that's doing, it's great to be able to kind of sniff the protocol and see what's up. Serial protocols themselves are also significantly difficult to reverse engineer. Some of it is just because we're dealing with ancient technology, and that very few folks still remember what a serial port is or how to hook it up. A lot of the deals with serial ports today is just a USB connector. You just plug in the USB connector and it magically works. But in a lot of this older equipment, we actually have, data terminal ready, data, request to send, clear to send kind of signals that we need to understand exactly how they work in order to enable the device. Otherwise, it won't work. Now, the use of logic analyzers with protocol decoders is your savior here. The big mambo daddy of all protocol decoders is a device from Agilent. It is a decoder that understands how to do like E2, E3 signals, T1 signals, telephony signaling mechanisms. And they're expensive. I mean, they're $20,000, $30,000 for one of those things. So if you can use some of the low-end logic analyzers like the SAILI units to help you understand what's going on, that's a good thing. Saves you a lot of money. Now, obviously, again, we can't emphasize strongly enough, check your voltages. This one happens to be the device that we were getting ready to do the RE on, and what voltage does it show? 9.6 volts. Now, why was it running at 9.6 volts? Turns out it had a pack of AA batteries that were running it. And that's the raw voltage off the AA's. And then it would go through various buck transformers and step downs and filters and everything to get it down to the 3.3 volt that the actual circuit used. But that meant that you had 9.6 volts floating around in the system, and you had to be very careful about what you plugged into, because that will definitely toast a serial port in a heartbeat. Now, again, remember, voltometer may not necessarily do what you need it to do. If the voltages vary quickly, you may not be able to see the spike in the voltage, in which case we have to drop back and take a look at it through a digital storage oscilloscope or something similar. Now, once we have it hooked up and we think we've got it, at least the voltage that we're trying to figure out, then try to see if you can get the device to send any data and watch what happens. Does the voltage change significantly? Or does something else weird happen? We'll see. We'll talk about this particular one where something else really weird happened. All right, so let's capture some data. This happens to be the output from the SALA unit. This was the transmit side, this is the receive side. So they're not lined up exactly like that. You had the transmit side and then you had the receive side. It was a half duplex connection. The bit width, when you actually set on and measured these bit widths, you found that it was roughly 56 kilobits, but not exactly 56 kilobits. It was 59 kilobits in some cases. So some of that has to do with they're not using a good solid crystal reference. Sometimes if they're doing phase lock loops and they're trying to generate the voltage, they're trying to generate the clock using a phase lock loop, sometimes the phase lock hasn't really happened yet, and therefore it will be a little wonky in terms of the frequency coming out of it. But it was roughly 56 kilobits, and there was some drift in it, but that was something that we could easily take into account in the SALA unit. Now, when you're trying to do a protocol decode, if your logic analyzer supports multiple protocols, try and switch. You've captured the data, just simply switch the interpretation. If you look at it as CAN bus, if you look at it as I2C, if you look at it as normal RS-232 async, those kinds of things can be really helpful just to be able to see it. How many pins are involved with the signal? Is it something that I can see in just 2 pins, in which case it's probably an RS-232, but does one of the pins look like a clock? When you hook it up to the SALA units, you're going to see this thing going ting, 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 and that's probably I2C. So when you start doing interpretation for I2C, you'll be able to decode the master and slave interfaces. You'll figure out what the I2C ID is, and little tools like Arduinos are wonderful at being able to do decode on this kind of stuff. Generate the actual I2C clocks, the SPI clocks, and then be able to get the device to talk to you, even though it's maybe kind of isolated from the rest of the circuitry. Of course, when we were taking a look at that particular protocol, there were some really strange things about the protocol. If you take a look here, you'll notice that and let me see if I can get this to show up over here. Whoops, wrong way. You'll notice that there was no voltage over in this section, and then suddenly the voltage went high for about 2,000 milliseconds, so about 2 seconds. And then it started clocking data. Now, this looks a lot like something called mark after break. So when you're looking at mark after break protocols, there are certain types of protocols that use this particular technique. So we were originally thinking that it may be a mark after break protocol. Then as we got a little bit further into it, it turned out that it didn't match any of the known mark after break protocols. And when we took a look at the data sheet, it turned out that this particular part didn't support mark after break communications protocol. So that helped us a lot by being able to rule out what we knew it wasn't. We didn't know what it was, but at least we knew it wasn't mark after break. Now, and taking a look at it, because of that weird, it was off and then suddenly it went high and then it started clocking data, it looked a lot like it might be bit banged. And when you're bit banging a port like that, that would also explain a lot of where we were getting some of the drift in the clock frequency. If you're bit banging the ports, you might be off a little bit, in which case it might look like 56K plus or minus a couple of K bits per second. And so it looked like, yeah, maybe this is bit bang. Okay, well, this is going to be interesting to try and figure out what this protocol does. Fortunately, there was some weird things about the protocol that told us that it was not quite bit banged. It turned out that, of course, the voltages started at 0. And because the voltages started at 0, we looked at the part and we found out that the part had 2 serial ports on it. So we suspected they were using one of the serial ports for the communications channel, but serial ports, when you enable serial ports, there's a voltage that's constantly available on either the transmit or receive pin, depending on whether it's connected as DTE or DCE. And in taking a look at that, we go, okay, well, that's really weird because there's no voltage at all for extended periods of time, and then when we trick it to do something, the voltage suddenly comes on and it starts clocking. We took a closer look at that. We found out that although it looks like a break signal, that high signal that would come out, it really wasn't mark after break. And then it meant that basically if we wanted to inject a new command, we're going to have to figure out what the pattern is and follow the pattern. So the goal for this particular case was to be able to get into the communications protocol and start injecting commands that in some cases might confuse the device, in other cases might do something special in the device that we can't really get into the details of. All right, so we used a microcontroller to do a lot of this testing. Turns out in this particular case, it was a CC3200 from Texas Instruments. The nice thing about this one is it had the right voltage level. It was all 3.3 volt. So we didn't have to do any level shifting. We didn't have to get any special circuitry out there to handle 3.3 to 5 volt level shifts. Also, this gave us Wi-Fi and JTAG on the embedded board, so we could actually have some options for interfacing to the micro and then kind of watch what's going on. We did opt in this case to use the Arduino-like Energia, or Energia, depending on how you pronounce it, I guess. This looks like Arduino code, and it sits on top of TI RTOS, so we can get it to do fast things when we need them to be fast, but not have to sit there in Eclipse and our minds go numb as we look at the Eclipse code to basically boot the board and do all the rest of the stuff with it. So Energia was a great solution for this particular case. Now, in the first try, we said, okay, well, we think we know what we need to do. We need to inject some serial port-like stuff. We knew we wanted to isolate our circuitry from their circuitry so they would not know that we were there. So we basically made our equipment look like a diode. Well, we used a diode to keep it from being able to be detected by the devices that were communicating with each other. And it turned out that if we didn't do that, or if we used a diode but then didn't do any additional isolation, we ended up with this weird thing. You'll notice those are not nice square edges. That's bad. That says that we would sometimes get some things through, but other things wouldn't come through. And it was all mystery meat until we put the scope on it, and then once we saw the scope, we go, oh, that explains it. Also, weird thing, the voltage levels here, instead of 3.3 volt, this was 1.8 volt. So it was a little strange that we would see some big change in the voltage there. So the fact that the voltage got cut in half, the edges looked horrible, this is not a good thing. We have to figure out some other way. So we went to a high-speed Schottky diode, and the high-speed Schottky diode can handle the frequencies. So that seemed to fix the problem for us. Again, because it's a diode, we basically isolated ourselves from the signal. They couldn't tell we were there. We could inject commands into the system and see what happens. We also needed to power the microcontroller. So what we wanted to do we wanted to have this as a box that would basically just plug in line with the thing that we were doing the testing on, just to make things easy. That way we could upgrade the system in a matter of like 20 seconds and put our box in the middle and then start looking at signals going back and forth. We needed to power the micro and to keep the signal at the same reference ground. This is a tricky thing. We definitely want to make sure that the ground being referenced in the controller, the real controller, is the same ground we're being referencing in our circuitry. Otherwise, we get ground loop problems and things just go to hell in a handbasket. So what we did was, remember that 9.6 volt power? We pulled that 9.6 volt power, ran it through a buck transformer, that's that little white thing you see down there, and converted it to 5 volts to power the microcontroller. So if you powered the microcontroller through a 5 volt USB connector, if you powered it with 3.3 volt, it didn't work. At least not for our application. If you powered it with 5 volt through the USB connector, everything worked fine. So we basically took the 9.6 volts, we pulled the power off of the connector, we ran it into this power supply, we then ran the power supply underneath into a USB adapter, which you can get from SparkFun. They're great. There's a little PCB that has a USB connector on one side and just through-hole solder pins on the other. And so we ran it into that, and it turns out that these, let's see, whoops, wrong button. These pins that you see here, that's actually the pins of the CC3200 sticking up through this PCB, through this perf board. And when we did all of that, it was amazing. We could actually inject new commands and watch what happens. As we were going through doing the decode on the protocol, we actually found out that there was some places where it was representing 100%. So you would see 100% on one thing or 100% on the other thing, and then the mix of 100%. So you would end up with 100% if you added the two of them together. Those were both being represented in 2 bytes for each one of those values. Also, now this is the thing that we were talking about earlier where you did a little research on the manufacturer and the people who held the patents. It turns out that the people who held this particular patent were both ham radio operators. And we were looking at the protocol output, and there was a weird thing at the end of the protocol that was a 16-bit value that changed drastically depending on what the input data was. And so we said, okay, well, this is probably a 16-bit CRC. And the problem is 16-bit CRCs, there's 24 different 16-bit CRCs. In this particular case, because the 2 people who hold the patent were ham radio operators, we said, AX25, which is a 16-bit CRC that's used in ham radio protocols. Let's try that. Sure enough, that's what it was. So, I mean, as a ham radio operator, I go, I bet you they're using AX25. Let's try that. And sure enough, that's what they were using. And when we went back into the data sheets and actually dug down through the data sheets for the Atmel part, we found that AX25 was one of the modes that it supported. So it's like, cool. So this is esoteric, detective work, but this is the kind of thing that you have to do when you're trying to be serious about reverse engineering something. But with this particular solution, we were able to inject commands complete with the CRCs, and lo and behold, the controller and the device it was controlling was unaware that we were there, and we were able to do our particular job, in this case, inject commands and make things light up and do funny things. Now, reverse engineering, kind of a summary here. Reverse engineering is an incredibly challenging problem. We have found some weird correlations. And that is, people who are really talented at reverse engineering also like to pick locks. I'm not sure why, but it's just a correlation. And some of the people who make malware, they will have like sets of locks sitting on their table, and that's what they'll do for a break, a mental break. They'll sit there and try and pick the lock. I don't know why, but it just happens to be a strange correlation there. It's a problem-solving issue. And if you like solving really, really tough problems, and you're familiar enough with the technology, the hardware underneath it, that you can then try to figure out, okay, so this is a serial port, but it's not quite a serial port. Why is it doing this? Then you'll be successful. Make sure you gather your tools, the hardware tools from places like iFixit. Again, the right to repair movement is a fabulous thing, because being able to source suction cups and pentalobe screwdrivers is a major pain in the butt. But thanks to iFixit, we can just simply buy it as a kit. Yeah, it's a couple $100 for the kit, but it's worth every penny. Understand what your goals are and when to declare victory. Is your goal just simply to figure out, oh, this is a Unix, or this is a Linux machine? My wife got upset with me with this one. We had a Samsung television. And there was a firmware update for the Samsung television. And remarkably enough, when you did the firmware update, you saw things go across on the screen like U-boot. And I go, okay, we're running U-boot on this platform. And there was a maintenance connector on the back that happened to be a serial port. Of course, the wife took a dim view. What are you doing to our TV set? Stop that. Get your hands off. I'm watching that. But it's kind of a cool thing when you understand the technology behind a lot of what's being built today. And certainly here at the Embedded Linux Conference, many of the devices that are being constructed are in fact using Linux. Anything that is an Internet of Things kind of device, it's got to talk to the internet somewhere. And if it's got to have a protocol stacks, you can get them for microcontrollers. They're expensive. But if you can get a free one for Linux, okay, it may be worth it to pay a little extra more money on the processor side and not have to worry about all this software that you'd have to write in order to handle repos and firmware updates and dealing with certificates and all that sort of business. So the other thing that I would say is understand the legal implications of what you're doing. As I say, in some jurisdictions, just taking the firmware off the platform using a SPI flash reader is illegal. Definitely check that before you start going down this path. For most of us, I mean, we think, well, I bought a PS3, and because I bought a PS3, it's my PS3, and I can do anything I want to. If I want to run Linux on my PS3, I can do that. No. The DCMA says if I go in and change the boot sequence, the boot firmware, to boot Linux instead of booting the PS3 operating system, I violated the DCMA. And, it's like, well, I own it? No, you don't. If you read the fine print, you really don't own it. You have an unlimited lease on the device. So always make sure you read the fine print. Now, because I like to live dangerously, what we're going to do here is I'm going to see if, I repopulated one of the serial ports on this board, and we're going to try it for the first time. And of course, I didn't sacrifice a large amount to the demo gods this morning. So I'm not sure exactly what it's going to do, but we're going to try it anyway. So what we'll do is, because I've repopulated the serial port, and I went through and I did measure some voltages to kind of know what sorts of things to expect. We'll run Minicom on this, and we will set it up for 115.2, which is usually the speed that a lot of these guys work. It'll be either 115.2 or 9600 baud. Those are the two that they tend to go to. Now, the one that we did the protocol RE on, that was 56 kilobits. That's a little unusual. 38.4 is even more unusual. But again, just by looking at the signal, we can figure out what the bit width is, and then calculate from the bit width, we can figure out what the baud rate is. But let's assume that we have here 115.2 running in 8.1. That's the other problem that we run into with serial. In most cases, it'll be no parity, 8 data bits, 1 stop bit. But that's not guaranteed. It could be 7 data bits, 1 stop bit, 7 data bits, 1 stop bit, even parity or odd parity. Odd parity turned out to be one that they used a lot in older equipment. So again, kind of look at the signal as it's coming across the scope and see if you can figure out whether you've got start bits and stop bits and how many of those things you have. So let's assume that we're running here, and I'm going to go ahead and power it up and see what happens. All right, now, with any luck, let's see what we get here. Oh, Yippee skippy. So we've got U-boot sitting here, and we can do a print env. And there's all the U-boot settings. So we now know, based on this version of U-boot, that there is no binary blob, no device tree structure because of the way the U-boot is put together. And we can then tell it to, let's just go ahead and live dangerously. Let's reset it. So it's uncompressing. So this is coming off of those two CRAM-FS protocols. Here, let me just blow it up a little bit here. Ethernet's running at 125 megahertz. Wi-Fi interfaces. Let's see, this one actually, it turns out that this is a MIPS processor. This one happens to be using a Cavium processor. And it's bringing up the Ethernet at this point. Let's see if we can get it to, there's a user prompt. Username and password. I haven't gotten to the point where I've figured out what the username and password is yet. Any questions? Is anyone still awake? Yes?
Real-time encryption of the OS is stored on flash, and you're like, how the hell do I do this?
Unfortunately, I cannot say.
I don't think as soon as I saw it,
Yeah, I'm both under NDA and classification issues. I can't say, but it was really tricky. It was like you implied. There was some real-time encryption happening and some decryption that was going on. You had to basically, so differential power analysis. Has anybody ever seen differential power analysis? So with differential power analysis, we can basically monitor the power rails. And it turns out it takes more power to decrypt a 1 than it does to decrypt a 0. So if you're watching it, you can actually pull 1024-bit RSA keys off of the device without too much trouble. Now, downside is you have to have physical access to the device. This is not something I can stand off a couple miles and figure it out. I have done things where, for instance, back in the day of CRTs, you used to be able to reproduce, with a good receiver, I could reproduce everything that was on the CRT from at least from almost a mile away. And so I could watch exactly what you were doing, what you were typing, all that sort of stuff. Of course, it was on my screen, it was an oscilloscope and it was all in green, but I could still figure out what you were doing, and I could see the commands you were typing, and when you entered password, I could see what that was. That was back in my day when I worked for some large unnamed government agencies doing Tempest, which was a way of being able to look at emanations and try to figure out what was going on out there. Other questions? Yeah. Oh, I don't answer your questions, I'm sorry. No, okay.
Have you worked with Radar at all as an alternative to IDA Pro?
A little bit. Have not had, once you pay the license, it's kind of like, okay, you got what you got, and you know what you got. That's another possibility. There are a lot of additional tools. I mean, I developed some really nice disassemblers in the past, and tools for doing analysis of code. We did have a large manufacturer of printers ask us to reproduce a piece of code that they had done. It was originally written in Italy. There were like 60 people who worked on the code for 3 years to develop this product, and then that division went under, and they said, can you reproduce the product based on what we have? Here, we have the source code. The source code was 17,000 lines of source code. And they were actually, what it was doing is it was taking a scanned image, converting it into a PDF, and then emailing it to somebody. So it was one of those things called a document sender. And it turned out that they were instantiating every line, every pixel as another object. I mean, this was like, and so you could tell the difference between Paolo's code and Giuseppe's code, because they all had their own particular coding styles. And we took a look at it. I mean, I have some tools that do, you know, reverse engineering of large code bases like this, and it broke all of them. It was horrible. But we said, you know what? We think we know what you want us to do. Let us try. And we were able to reproduce it with open source code, 2 people, 6 weeks. And we had 95% of the functionality working. And we knew how to solve the other 5%, and they said, that's enough. We've seen enough. Oh, by the time we finished, we had 50 lines of code. That was it. Total 50 lines of code. Everything else was just pipe this to this and do this thing. And it was like, you know, it was just a shell script basically, and we could reproduce this thing in like 50 lines of code. And the 50 lines of code was some Java that somebody wanted because they wanted to have a display. It was like, okay, well, we'll give you a display, sure, success. You know, what do you want? That was that was all the code, was just basically to do the display that they wanted to have this as success. Yeah. Okay, question.
One comment you did make was it's hard to find the earliest serial number and firmware you can find, because oftentimes security fixes come later.
That's right. Yep.
So like the TiVo 1, for instance, included the symbol table
Yeah.
in the image.
That's a good point. You know, oftentimes, I should have mentioned this. You always get 2 of whatever device you're going to hack. I mean, I guess it seems obvious, but because the first one, you're probably going to destroy. And then once you learn everything you need to learn, then you do the second one. But yeah, you always want to make sure that at least 2 of them fall off the truck so that you can figure out what it is. Question?
So let's say you're on the other side of this. Let's say you're an engineer building some IoT project, and the pointy-haired boss says, we need to make this thing hack-proof.
Given enough time and money, anything is possible. Now, the question is, how much time and money is it going to be? Understand that you know, when you're dealing with typical black hats that are going to be trying to take things apart, their motivation is primarily money. They're trying to hack credit card numbers or something. They're trying to get some money out of it. And if you make it sufficiently hard, they will give up and go on to a softer target. Now, at what point is it sufficiently hard? Well, that's up for debate. In the case of state-sponsored hackers, they effectively have no budget. And they have the best and brightest that they have been able to find, and there are some really clever people that are in that business. And if you're going against state-sponsored, they will own you. Eventually. It may take them a little while, but if they really want it, they'll get it.
That's why threat modeling is so important.
Absolutely. You want to know who's trying to hack your system. And unfortunately, today, a lot of companies don't spend enough time doing threat modeling. When you're trying to develop secure code, and that's the other thing that we do, we help people understand what it means to develop secure code. And so when you're in that particular business, you're trying to explain to them that the security engineering can cost at least as much as the total product, if not more, if you really want to lock it down. So now your threat modeling becomes a factor. You know, we're talking about risk mitigation here. What risks do I want to accept? What risks do I want to transfer to a subcontractor so it'll be their problem? I'm talking to you, Toshiba, you know, Toyota. You know, so you're going to transfer some of that. You're going to accept some of the risk. You're going to try and mitigate the risk by adding additional security measures in place. Obviously, when we're using things like TPMs, and secure data stores, that makes things a little bit harder. Obviously, and then of course, using TPMs, we need to understand which type of TPM, because the Chinese have their own TPM that have their own encryption algorithms in them. They do the standard TPM 1.2 stuff, but they also do something else. And it turns out that a lot of machines, a lot of laptops and things that come out of mainland China have the SX88 chips in them. And that's a different kind of TPM. And then you wonder, okay, is there a back door in there? But the reason they created that chip is because they were afraid that TPMs from Infineon and all these other places also had back doors in them. So go figure. Any other questions? Yeah.
With the production of consumer
Occasionally, what we find are some really interesting things. They call them door knock protocols. Have you heard of them? So basically, you hit this port, this port, this port in this order, and it unlocks something. Door knock protocols are really interesting to see them implemented. One of the easiest ways to avoid that kind of problem as you're trying to engineer a secure solution, peer review. I mean, it sounds stupid, but having more than one person look at it, go, what the hell is that? Why are you doing that? Is a great thing. I mean, you take a look at the numbers between proprietary code versus open source code. Proprietary code tends to have 9 times more errors in it than open source code does, simply because, if nothing else, it's because of the peer review. Now, that does not mean that open source code is impervious. Look at Heartbleed. That was a big one, and it had been in there, and everybody was using SSL for 5 years before anybody ever found it. It had been peer reviewed, but they just didn't happen to see that. Yeah.
In your experience, what do you think is a contributor worse to security? Greed or pride?
Mostly greed. Understand that when you're trying to build a new device that nobody's built before, or something that's supposed to be better than anyone else has built before, the market is, you're either number 1, number 2, or nobody knows who you are. We can easily say, okay, who's the number 1 bookseller on the internet? Amazon. Who's number 2? Barnes & Noble. Good. Who's number 3? Maybe. I mean, that's the thing. Once you get to number 3, nobody knows you. I mean, you might as well not even bother. So the problem here is that time to market is everything. If I've got this really cool thing and I need to get it out in the market, I need to get it out there before anybody else does, we take shortcuts. We don't do the due diligence. We don't do the security engineering. Understand, what's the mindset today? The mindset today is, let's say you've just bought your brand new iPhone X. What's the first thing you do? Plug it in. And then the garbage. Okay, I got, I use Sony, but that's a different. Tim Bird would actually be happy about that, since he works for Sony. But in any case, the issue here is the very first thing you do is you plug it in and you update the firmware. So manufacturers know that the very first thing you're supposed to do is update the firmware. So they ship it with firmware that has bukus of bugs in it, security problems, all kinds of stuff, just to get it into the distribution channel. Once it's in the distribution channel, they figure the first thing you're going to do when you get it home, you're going to plug it in, you're going to update it. So that gives them an extra 6 months, anywhere from 3 to 6 months in the distribution channel before they have to worry about anybody actually using this really buggy software. So that gives them an opportunity to fix it and then pre-position the update so that as soon as you update your phone, everything's good. Now, that doesn't keep you from jailbreaking the iPhone within 24 hours of them coming out with a new firmware, but that's a different problem. But that's the kind of thing, and that's the mindset that a lot of manufacturers are in these days. Even I had an OLED television set from LG, and the first thing you do is you update the firmware when you plug the TV in. Really? That's something, most people wouldn't think to plug in an appliance into the internet to update its firmware. Now, I always am suspicious about things like that, so I kind of turn on Wireshark and I watch what it does. But that's a different story. Anything else? Yeah, questions?
Both the tool set and the prevalence of reverse engineering RTOS that are not common or that are one-offs. For example, like the Western Digital hack.
Yeah. There are going to be cases like that. For instance, the Third People's Liberation Army, which used to be the name, they've changed the name now because everybody knows who the 3PLA is. But they had a captain that had been working at Seagate in Malaysia at one of their plants, and every hard drive that got shipped out had something special on the hard drive. They found him, they caught him. He pulled out his black passport and they deported him. But now we don't know how many of those hard drives got out before they found him. So those kinds of things, that's kind of a one-off. I mean, it's a very specialized system. You're not going to see it being done very often. And so, you know, fortunately, that's been so long ago now that most of those hard drives are already dead. But it's still the possibility, if you find a box, an old box. Not very common because it's always, you know, what's the payback? How quickly can I achieve the goal that I'm trying to achieve? And if I gotta custom create some whacked out thing to reverse engineer this stuff, it's just like, you know, is it economically feasible? If somebody's paying me, then absolutely I'll do whatever you tell me to do. Not that I'm a bad guy or anything, but you know, the reality is, if you're paid to do reverse engineering, that's what you're paid to do. And there are a lot of companies out there that do reverse engineering. Now, you know, obviously you're trying to do the quickest solution because nobody wants to hear that, well, you know, it's going to take me 6 months to figure out how this protocol works, especially with encryption. Encryption is really, really tough. Encryption is not the end-all, be-all, because it all becomes an issue of whether or not you can retrieve the keys. Data in use is a real interesting problem. It turns out that what we see in data centers a lot of times, as you start migrating VMs from one machine to another, they take all their memory and they write it off to disk. So passwords, keys, things like that that happen to be sitting in memory are now on disk, and it makes it real easy to find them. Not necessarily, not necessarily. And this is, again, to get it out quick, they did a kind of crappy job of doing their security engineering. So you find weird stuff like that. We have a cybersecurity class. We teach a cybersecurity class, and in that class we actually do this. We run a VM and we snapshot it, and then you look in the VM and you can actually find the password. Yeah.
Any additional resources or places to go to learn more on this topic?
Reverse engineering is almost always done as as kind of a temporary blog sort of thing, and the sites will pop up and then disappear as people start getting angry with them. You know, hey, you shouldn't have done that to my machine. I'm going to crush you. You know, that kind of stuff. So unfortunately, there are some books that are out right now on reverse engineering. In particular, there's a nice one that just recently came out on reverse engineering Linux binaries. Definitely an interesting one. You can pick it up on Kindle, actually. I just got it myself. I'm still going through it at this point, but I forget right offhand. Send me an email, mike@thePTRgroup.com. I'll tell you who it is. Okay, we're out of time. I appreciate it. Thank you very much.